When it comes to developing sectors and industries, space exploration is easily the one which makes the most headlines. In recent times, robotic explorers have become our eyes and hands on distant worlds. From the Viking landers on Mars to the Mars Science Laboratory's Curiosity rover, each mission has pushed the boundaries of our knowledge and engineering prowess. University teams now carry on this legacy on a smaller scale, translating decades of aerospace research into innovative student-led projects. We are the Makercie Rover team from the Netherlands, made up of students from the University of Groningen, Hanze University of Applied Sciences and the University of Twente, and this is our video for the 2025 edition of the European Rover Challenge. We will be presenting a rover, Vulcan, and its companion drone. Under the supervision of robotics expert Dr. Bahar Hagigat, Makercie is led by William Buitenhuis, who oversees the general progress and activities of the team and acts as a contact person between the team and the organizers. Makercie itself is organized into 7 sub-teams that together power the Vulcan rover for the ERC 2025 in Krakow. Hardware contains the mechanical and electronics sub-teams, led by Bas Boersma and Andrea Popescu respectively. Mechanical works on the chassis and mobility systems to conquer rocky terrain, while electronics works on creating reliable power distribution, sensor integration and wireless communication. The software teams, led by Luca Chavala on navigation, Sara Boda on maintenance, and Sebastian Serengi and Mathis Fischer on control and communication, develop autonomous mapping, localization algorithms, and robust teleoperation interfaces. Our drone sub-team, headed by Laura Quiros, develops our UAV companion drone for high-resolution site mapping, real-time obstacle detection, and strategic waypoint planning. Above and beyond, the science department under Jona Balint designs and executes experiments for competition, including, but not limited to, soil sampling protocols and imaging granulometry, to meet the ERC's scientific objectives and validate rover collection data against real-world planetary idioms. Meanwhile, the non-tech department, from HR led by Araf Bandal to PR and acquisitions under Theodor Shobov, secures funding, handles outreach and creates competition media to get the word out. Furthermore, our presentation team focuses on developing documentation required for internal team activities, as well as those needed to be submitted to the ERC for qualification. As we are mainly bachelor students in a very international environment, it's natural that a lot of our members go elsewhere for their studies. So we need to make sure we retain the knowledge gained. To sustain this amid continual turnover, we make sure that veteran team members guide newcomers through CAD modeling, fabrication workshops, code sprints and more. Our custom-built Marshart at the Energy Academy Europe enables field trials, while partnerships with Batenburg-Benen, Viasat and Innovation Cluster Drachten supply expert consultancy and explore commercial spin-offs. Of course, we can't forget the Hanze Makerspace, where we're able to turn our visions into reality and build our rover and have team meetings. So what has motivated us to participate in this challenge? 2 years ago, in 2023, our newborn team won the Remote Formula Edition with a laptop and a lot of Zoom calls. Coincidentally, this was also our first time participating in the ERC, and we were pleasantly surprised with our result. Last season, in 2024, in our first on-site outing, we finished 29th out of 69 teams, having only narrowly missed the threshold for the qualification to the next stage, and learned more in a few weeks than in an entire semester. Those results have lit a fire in us. If a young Dutch team can already stand on the leaderboard, how far can we push when we iterate for another full year? We are motivated to continue with iterating and making necessary adjustments when the bar is raised every season. Our team is also constantly evolving. We are growing, learning from our shortcomings, understanding how to work more efficiently as a team, and receiving more support and recognition from our partners and the university community. Especially with the establishment of our new Students Association, GEARS, we are looking to further challenge our students. Meet Vulcan, our rover, engineered by Makercie for the European Rover Challenge 2025. Since the ERC 2024, it has undergone numerous design iterations which have greatly improved its capabilities, most notably its upgraded chassis design. Bigger, stronger and simply better. With more space for electronics and cargo, a better rocker suspension system to deal with rocky and uneven terrain, and entirely new wheel hub designs, our chassis is sure to support the weight of responsibilities it faces in its upcoming ERC missions. Starting off, designed with new safety coupling to protect our smarter and stronger Maxon motors, the wheel hubs feature a number of new designs, such as our custom printed TPU wheels, specifically designed to absorb the impact of the rough Martian terrain. Each wheel, furthermore, features non-back drivable worm gears, holding their position even when power is off, ensuring stability in any terrain. And finally, special covers are used to protect the motors from the elements. Next up, having undergone the most changes, is our robotic arm, After 2 prototype iterations, the design has been greatly optimized, changing from 6 degrees of freedom to 5, ensuring it can complete all required tasks simply and efficiently, minimizing its weight and complexity. Additionally, its placement has moved to the front of the rover for a greater range of motion and better positioning to collect samples. We even simulate every movement beforehand in our Jetson-based system, so the robotic arm never collides. And of course, the arm is incomplete without its new gripper design, complete with pressure sensors and a morphing design to pick up even the most oddly shaped object we may find on Mars. Moving on to our software control systems. Every movement of Vulcan is guided through our custom-built ground station, built with NASA's OpenMCT and Tauri. The control interface offers real-time feedback on power, temperature, and wheel speed. With every component connected via a robust CAN bus system and dual communication channels, Wi-Fi and radio, we're always in control of the rover. This brings us finally to the components tying everything together, the electronics. We design custom PCBs that distribute power from the battery, control the motors in the arm and chassis, and monitor the rover's important vitals through voltage, temperature, and position sensors. If any subsystem draws too much power, an automatic relay kicks in, cutting power before damage occurs. Each channel has its own fuse, power sensor, and relay, and the main relay is controlled by an emergency button. It makes the whole rover stop instantly. And for issues with individual parts, smaller relays safely move affected parts to neutral positions, then shut off, without affecting the rest of the rover. Integrated with remote control, beacon light, and emergency button, this allows us to protect both the rover and its surroundings and ensure safe operation. These PCBs are a great improvement over the breadboard wiring of the ERC 2024. However, further iterations are needed. With the increased complexity of the rover, smart control of the motors is essential. For this reason, movement is currently restricted to only one single motor at a time. However, individual tests confirm movement and functionality in our mechanical designs, and our emergency stop button functions as expected. We plan to make the necessary modifications to our PCBs and make our rover Vulcan fully operational by the time of the ERC 2025. Built on the PX4 development kit and powered by ROS, Makercie's UAV features a self-assembled design and modular payload. A 32-bit flight controller fuses GPS, IMU, and optical flow data to keep it steady even in winds up to 7.5 meters per second. This has been confirmed through simulation tests in a custom gazebo environment aimed to simulate the task of the competition. This provides us a safe testing environment to develop our own software script used to control our UAV using GPS location, supported by Aruka marker detection. Using a downward camera to detect these markers, the UAV can spot interesting features in its environment and accurately find its landing position. This system has been further tested in real-life environments. The drone can be seen to take off and fly along all 3 axes before returning home and landing safely. We have additionally included several safety procedures. Our pilot can switch instantly between autonomous waypoint missions and manual RC control via a dual redundant 2.4 GHz link, complete with return to home and throttle override failsafes, allowing us to take over control, force the UAV to auto-land, or turn off motors entirely. With its modular design, robust safety systems, and seamless handoff between autonomy and remote control, Makercie's UAV is fully mission-ready for ERC 2025. The Rover sampling collection system works through a combination of various components. The robotic arm will be used to pick up rocks and wreckage samples from the terrain and deposit these on special boxes on the rover. The gripper is modular with interchangeable anti-vectors and built-in pressure sensors to handle both delicate and heavy objects securely. Additionally, we have integrated a deep drilling system capable of reaching over 30 centimeters below the surface. The drill uses a custom bit and a 2-stage linear rail driven by a brushless motor for power and control. Furthermore, we use a pH sensor module for science mission and vibration-assisted sample storage to ensure clean data collection. Samples are deposited into specialized containers, isolated, secure, and designed to prevent cross-contamination. These tools work seamlessly with our ROS-based software and BioIK inverse kinematics, enabling precise manual control during the competition, and once our next PCB prototype is completed and simultaneous general movement has been implemented, integration tests will be performed to confirm full and complete functionality.